Howdy, this is your friendly neighborhood physics teacher here, and we're going to talk about a little bit more about rotational motion, but we're going to talk about pretty much torque and momentum and how they deal with rotation. Now, torque is just a rotating force. That's all it is. And of course, momentum is moving mass, so if things are rotating, you're going to have a moving mass also. And we can kind of see that in our picture with here of the arm. So if you think about an arm, you have a ball and a hand. So you have the force of the ball going down against the arm. You have the force of gravity of the arm, but then you have this force of the bicep that's keeping the arm straight out. You're just sitting there holding your arm out, and all what's force is causing that is your bicep. You can sit there and just hold it, and you can kind of feel your bicep. You sit there and poke your arm right there, and you can kind of feel that your bicep is engaged, even if it's not very much, but you can feel a little bit of tightness there. And what you have to think about is what if your arm starts to rotate, and basically you're talking mainly about your lower arm right here, where would your pivot point be? Kind of thing. And so, of course, it'd be your elbow. That's your, you sit there and pick your arm up and down, arm up and down. That's your pivot point. So anytime you're dealing with torque, in this case, you have to figure out how far the force is from the pivot point. So that's why you're seeing distance there, and then, you'd have to add those two distances there. Now you're wondering, like, why is the force of gravity here in the middle of your arm? It's because anytime you have a beam, and your arm can be considered a beam, you take the force of gravity comes from the center of the object, kind of like the center of mass project, little activities we did at the beginning of the year. So that's just a kind of brief overview over torque real quick. So we're going to talk about torque, how torque and angular acceleration interact. So basically, when your arm was standing like still right there, it's equilibrium, it's balanced. We'll talk a little bit about center of mass just to refresh how things balance, and then we'll get into angular momentum and conservation of angular momentum. So torque. Torque, like I said, is just a rotating force. What force is applied to make an object rotate? Anytime you're dealing with a monkey wrench or pliers or anything like that, and you're having to physically rotate the nut, you're applying force. So you're applying a linear force that's causing an object to circle. And think about it. You can easily think about a door. A door, you need to open and close a door. You have to apply a force, and the door rotates. So that force gets turned into torque. Why do you think the door handle is is on the farthest point away from the hinges? So you have a little girl here that's pushing on the edge of the door, and you have a gentleman here that's pushing near the center, not even near the center, near where the pivot point would be. And it's because the longer you have that distance, that R, from the pivot point, the less force you need to actually make it rotate. That's why you see all these like wrenches that are like really, 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 really long. And so you can sit there and not apply as much force, but be able to rotate your lug nut there. And so that's why you don't want to sit there and grip your wrench like right against the neck. You want to do it near the end, so you don't have to apply as much force. Same thing with like pushing the door. That's why your door handle is on the very farthest it can and not like the center of the door. So I want you to try that. Go to a door and sit there and try to, push it near the edge versus push it closer and closer and closer near the hinge. And light doors, it's going to be hard to find, but if you can find a heavy door, like the doors in school, I always sit there and have y'all try it. You can tell a big difference. So that you do have a torque equation. This equation is on your formula chart. It's actually 1, 2, 3, 4, 5, 6, 7 from the bottom. It's 7 from the bottom on your long list. And it has, so it looks, and adding a little bit to it, it has a parallel little symbol there. And also, if it's not parallel, it continues and you use sine theta. And so that's what, oops, didn't mean to jump. That's where your equation kind of looks like. So your force has to be, not parallel, perpendicular. I do apologize, guys. So it has to be perpendicular to the object. And you saw then, going back to the arm aspect here, so it is perpendicular to the object. If it's not perpendicular to the object, you have to use your sign and take the angle into consideration. So as your torque increases, your force has to increase. And but also, so it's something's got to give. You have a relationship here. So if your torque, and that is a Greek letter tau, capital tau. And so if your torque increases, your force either has to increase or your distance either has to increase. So that's why you can do less force but longer distance and still get the same amount of torque you need to rotate. So only your tangential component force causes a torque. So only that, only the part of the force that is truly perpendicular to the object causes the torque. So if you have a guy sitting here and you're trying to make the merry-go-round turn, if you're just pulling out, it's not going to end up rotating. But that's why you sit there and do a good push. Yes, you might be pushing at an angle, but only that force that is truly perpendicular is what's causing the rotation. So that's why you do have to take that sine theta into consideration. So it does lead to more general information definition when you can just sit there and do your radius times your force of sine theta, and it will always be sine theta. So yeah, there you go. Now, if the torque causes a counterclockwise angular acceleration, it's positive. If it counters a clockwise, it's negative, just like how we learned about the motion in our slide before. And what you'll notice is that the linear equation, there is a rotational equation that fits it. So we have A equals F over M, so it's your linear acceleration equals your linear force over mass. This formula is on your formula chart. Is 1, 2, 3, 4 from the top on the big list. It just kind of, has a little bit of different things to it. You can add the summation, your little arrows that just telling you it's a vector, and you also can see it as net. So that's how it looks like on your formula chart. Now, you just change your variables to the rotational part. So your A equivalent is alpha, and then your force would be equivalent to torque, and your M would be equivalent to your moment of inertia, which is I. And so to be a little bit more specific, you say that your torque is force times R, which if you remember, all your V or your omega equals R times V, theta equals X times R. So it pretty much, if you're trying to get to the rotation, you just multiply the linear times the radius and you get your rotational part, except for your moment inertia. Then you have to do it squared. So basically you get that your torque equals your I alpha. That formula is not on your formula chart. So that is either something you would have to sit there and derive, or make a or I would put it on your one pager. So again, linear versions is your mass, your alpha, your A acceleration, F force, then you get your I for moment of inertia, alpha for angular acceleration, and tau for torque, which is your rotational force. Just like with force, you have your equilibrium balance. So if your net force is 0, your object's either not moving or moving at constant velocity. It's the same thing for torque. If you have 0 torque, the object's either not rotating or it's rotating at constant velocity. 9 times out of 10, it'll just be not rotating. It'll be balanced. Like if you think of like a little seesaw here, that means if you have a person over here and a person over here, it's balanced. And example A over here. And so you have the force that the mom's putting up, force the dad's putting up, and the force that the little kid's going down, everything going up has got to equal everything going down. So it's still the exact same thing. To kind of balancing out that way. Now, if you have and they're making like the little kid, I think in this case, axis rotation. There we go. So in this case, the axis of rotation is saying, so basically, if the dad drops it, it's going to rotate around the mom's hands. And so the force that the dad's putting and the force that the kid's putting are kind of counteracting, and you don't have to worry about the force that the mom's doing because it is the axis of rotation. If there's a force at the axis, you don't have to worry about it because it's not going to make it rotate. And then when you flip it, you have the force going up versus force going down. And again, you don't worry about that because it's at the axis. So if she lets go, it's obviously going to fall. Same thing with this. If the dad lets go, obviously it's going to fall. So, and you can see that since the dad is closer to the kid, he has to apply more force versus if the mom is further away from the kid, she doesn't have to apply as much force. For like signs hanging, you have the typical, you have like a sign kind of hanging, something like that, and you have a string holding onto it. Sign. They like doing stuff like that, and that's equivalent to like the lamp here. So you would have to sit there and figure out, what's, the tension there, and you have some type of force here with the force of gravity. So when the forces have both your vertical and horizontal components, you do have to break it down to its X and Y components. So you can figure out that there's no torque and the net force is 0. So that means everything in the Y and X are balanced. So basically that and that are somehow balanced, and that are balanced. So there has to be some type of balance there for the lamp not to move. And the same thing with the sign here. So you have a force of tension going up. You'd have to break it down into its X and Y components to counteract the force going down, the force of gravity going down on the sign. Balancing things. You saw our pre-AP physics do a torque project, which was making a mobile. That's basically what they did here. And so they had to pick, we told them to make math a little bit easier for them, to put like the pivot point, so that would be the pivot point actually in the center. But in this case, it's not, because, they don't want to make math easy for AP. And so you would have your R and then your mass, your R and your mass. And as long as the object is not rotating, it's not moving back and forth, this torque would end up equaling that torque. So torque 1 would end up equaling torque 2. And you could just sit there and do your M1 X1 equals M2 X2 and see that it balances. And your R is from the pivot point. We kind of did this already, sitting there trying to find the center of mass of an object, and you can find the center mass of any object, suspending it from different axes, and wherever they all cross is the center point. We kind of, like said, we did that already at the beginning of the year, but just a refresher. Now, pulleys. Pulleys do have torque since they do rotate. If you have a mass, so this is like the physical picture. So this is exactly what's happening. You have a pulley with a mass that's being pulled down due to gravity. And so if you're just focusing on the free body diagram of the object, you have force of gravity going down, tension going up. Force of gravity is more because it is moving in the downward direction, and it's not moving as fast as it can because torque is counteracting. Now, if you're doing the free body diagram of the pulley, you just have the tension going down. Now remember, this tension, he's right, dude, this tension and this tension are the same because it's the same rope. So again, so you would kind of have to sit there and do probably have to sit here and do your free body diagram to figure out your tension, and then you can sit here and then you could figure out your torque that way, because it would be your radius times your tension to get your torque. So you can sit there and do it that way. So yeah, there you go. Just seeing how things can interact. And you're still just drawing free body diagrams, and it's just a normal force. It's just the force is causing something to rotate. So you do have to take that radius into consideration. For angular momentum, we represent an L. Just like momentum, we represent a P. It's like we're running out of letters here. And if you remember, your momentum, which we learned about just a few weeks ago, is mass times velocity. So we're just changing things equivalent to rotation. So your mass is equivalent to your moment of inertia. Your velocity is equivalent to your angular velocity. So you're literally just replacing those. Woohoo! And the units stay the same. So yeah, so there we go. And that units stay the same. That squared should be on the S, not the M. Fun trick there. Sorry about that, guys. So using a little bit of algebra, you can actually figure out the particle movement of the circle. And so you have your breaking down, going back to mass and velocity, you're just timesing it by R. You can get that your R is just times your momentum. So again, going from linear to angular, you're just multiplying it by radius. If you haven't gotten that yet, hopefully you're getting it now. And again, perpendicular does play a big part to it, so it needs to be perpendicular. If it's not, you do need to put sine into the mix. Why do I keep doing that? Why is mass squared, meter squared? No, meters is squared. Nope, meters is squared. Because the reason is because you have your mass, you have your I, which is mr squared times m over s. Your mass is, so why isn't your kilogram squared then? Oh no, because it'd be kilograms meters squared over, so it should be cubed. Let me check on that unit. That unit's confusing me. I need to check on that unit. Okay, so again, I'm gonna double check on that unit for you after this video. And so here we go, continuing. So you do have to break things down into its x and y components, so it can be perpendicular to the direction from the object. So you can sit there and do the rate of change, which would be equivalent to your rotational impulse. But it'll just be your torque is your mass times angular acceleration, your angular momentum. And that's just relating it back to your Newton's second law. So it's just your change in momentum over time. And this is what I was telling you about in the last slide. If you have your, if you have like a rolly chair that can spin, or just a spinning chair, you can see that as your arm is out and you're rotating and you pull it in, you're going to end up going faster because you're shortening your radius. You're bringing the mass more towards your pivot point, because in this case, the chair would be your pivot point. You're bringing that in, you're shortening your radius. And so you need less force to actually make you rotate. So if you keep the same, and you'll keep the same amount of force, you're just shortening radius, so you'll be able to go faster and faster. That's how like ice skaters work. And that's why they spread out their arms to kind of slow themselves down. And so your conservation of angular momentum. So as the moment of inertia decreases, the angular speed will increase. So that's an inverse relationship. and your angular momentum doesn't change. So it's also, so like if you have a rotation collision, so in this case you have a turntable that's already turning and you have a disc or a vinyl that you sit there and drop, when it collides, it's going to actually start rotating. So again, it's kind of like if something is moving and hits something that is moving, makes it move, maybe at a slower rate. Dealing with momentum, it's the same thing, it's just going to cause it to rotate. Now, how it relates back to work and power. The work done by torque, this formula is not on the formula chart, but if you remember, your work is just your force times your distance. So again, you're just replacing things angularly. So angular force is your torque, angular distance is theta, and it needs to be your change in theta because how much it changed. So that's why it's a delta theta. Even though on your work equation, if I can find it, I'm looking at the formula chart. Where is it? Your work equation is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 from the top. It just says distance, but you'd have to do your change in theta in this case. So your work energy theorem still applies here because you have rotating energy. You would still have, so you can still do your delta K equals your work. It's just if it's rotating, it's going to end up being your 1/2 I omega squared equaling your torque change in theta. So the same exact equations work from linear to rotation. You're just converting them into your angular counterparts. The same thing with power. So your power is work over change in time, and you can plug in for power, and you just get that and then you can take a step further and see that equals your omega. You can see that power just equals your torque times your omega. Again, I didn't show you this when we talked about power, but power can equal your force times velocity. Again, if you're working just with the linear part, if your power is work over change in time, work is force times distance over time. Again, that's velocity, so force equals velocity. So you can see how those two interact. Now, vector nature of rotational motion, knowing how, which direction vectors go, since you have things going forward, going backwards, going left, going right, it all deals with the direction of the axis, and you can use your right-hand rule to kind of figure out what sign is it going left, right, positive, negative, and all that fun stuff. And I know if you're left-handed, you're naturally going to want to use your left hand, but this only works for right hand. So this is called a right-hand rule for a reason. You have to use your right hand. Even if you're left-handed, take a deep breath and use your right hand. And you want to put, so think about using your right hand. If it's so the wheel in this case is rotating towards the screen and then out of the screen. And so that's the direction you want to put your hand, your fingers. Your fingers are going to go like the direction of the motion of the wheel. And you see that your thumb is going towards, in this case, it would be towards your left. And that is the direction that your linear momentum and your angular velocity is going to go. But your tangential velocity is going to end up going the direction of your hand. That kind of helps you there. And you can see and you can do the same thing for torque too. So if you put your fingers in the direction of the force, the direction your thumb is, that's the direction the torque is going. So it kind of helps you there. Conservation of angular momentum means that the total angular momentum around any axis must be consistent. So if you have in this case, we have like two axes going on with dealing with a gyroscope, it has to be sit there, and that's how you can sit there and it stables itself. So you have in this case, you have the angular momentum going to the left, you have your force going, or your velocity and force that's making it rotate going into the screen, not counting your force of gravity pulling it down. So that's why your torque would end up being, your torque would either going into the page or out of the page, because that's what your fingers would represent. There you go. So just a quick summary. So you do have a rotating force, which is called torque, and it can be your force times your radius, or force times radius times sine theta, just according if it's already perpendicular to the motion or not. And you can relate it back to Newton's second law. Now, this equation and this equation are on your formula charts. This equation is not on your formula chart. But again, it's just doing your mass times acceleration, and you're just putting it into your rotational. Now, anything that's equilibrium, everything has to be balanced. Same thing with force and torque. The net force, the net torque have to be equal to 0. An object's balanced is when its support at the center of mass. Getting into your angular momentum. Now, this formula is on your formula chart. What did I say? It's 1, 2, 3, 4, 5, 6. So this one is on there. It's 6 from the bottom on the big list. This one is not, but it's just using the linear. So it's using mass and velocity, multiplying it by r. This one is not. Please work. Pen. Lord have mercy. That one is not. And this one is. It's just in a different form. It's solvent. It has your delta L equals your torque times delta T. So that's how it's written. And that one is 1, 2, 3, 4, 5 from the bottom on your big long list. So yeah, so there's that is related to how torque and angular momentum relate back to Newton's second law. In the systems with no external torques, angular momentum is conserved. We do have a work equation. That formula is not on the formula chart, and neither is this one. But rotational quantities are vectors that point along the axis of rotation with the direction given by the right-hand rule. So yeah, so that's just a quick overview. If you have any questions, please let me know. And the next video will be the FRQ for the College Board. Hope you have a wonderful day. Bye.